Alright, so here we go with the review for the Thermochem exam. The first question, we're looking at a gas sample that is going to be changing volume and losing heat. So we're working with the equation that the change in energy is equal to heat plus work. Alright, and we're given actually the change in energy, 500 joules, and we're told that the system loses 180 joules. And so the rest of the energy change has to be due to the work. So there's a couple different ways you could go about solving this. The first thing to do would be to isolate the work on one side of the equation, so we subtract negative 180 from both sides, and we end up with negative 320 joules equals the total amount of work. So we have to figure out, based on the problem, how much of a volume change, which is where the work is coming from, it's the gas pushing against the atmospheric pressure and expanding, that makes up this other 320 joules. So we need to convert the joules into liter atmospheres, or we could do the liter atmospheres calculation and convert it to work convert it to joules at the end. But if we remember that, as it says here, 1 liter atmosphere is 101.32 joules, and we take the negative 320 joules and divide that by the 101.32 joules, that converts the unit from joules into liters atmospheres, and we get a number of negative 3.158 liter atmospheres is the amount of work that was done. That equals W. So since the work here equals the negative, remember that work equals negative of pressure times the change in volume, and the change in volume is the difference between the final volume and the initial volume. We're looking for the final volume. So work equals negative pressure times final volume minus initial volume. We have the pressure, we have the initial volume, now we have the work in terms of liter atmospheres. So negative 3.158 liter atmospheres equals the pressure, negative of the pressure, which is 3 atmospheres, times the final volume minus the initial volume, which is given as 5.8 milliliters, or 0.0058 liters. So from here I can divide both sides by negative 3, and that's atmosphere, so that cancels out the atmosphere unit over here, and we get 1.052. Since we've got two negatives, it becomes a positive number, equals the final volume minus 0, and this is liters now, sorry, because we canceled out the atmospheres, 0.0058 liters. And then if we add 0.0058 to both sides, we end up with 1, so the final volume, sorry, went off the screen there. The final volume up here is going to round to 1.06 liters. If we have 2 samples of water at 2 different temperatures, we add them together and we get a final temperature of the mixture of 50 degrees. Then what was the initial temperature of the water in the beaker? So again, there are different ways to solve this problem. What I think is the most straightforward is to keep in mind that the total amount of energy in the mixture assuming no heat is lost in the process, the total amount of energy in the mixture is equal to the energy of the sample that was in the beaker plus the energy of the sample that you add to the beaker. So I'm going to write that as E total equals the energy of sample 1 plus the energy of sample 2. And just for the purposes of the problem, we'll call sample 1 the sample that's in the beaker, and sample 2 the sample that we add. So the total energy we're actually given in terms of degrees Celsius, 50 degrees Celsius, times the mass of the mixture, which is 830 grams, because it's 830 milliliters of water. Water's density is 1 gram per milliliter, times the specific heat of water of 4.184 joules per gram per degree Celsius, and that is equal to E1 plus E2. So E1 is the mixture in the beaker, or the sample that starts out in the beaker, and it has a temperature of T. It has a mass of 488 grams, and we find that because the total is 830. The amount that was added was 342, so the difference between those, what had to be there to begin with, was the 488, and that's times 4.189, the specific heat of water, and that's plus sample 2, which was at 20 degrees Celsius, 342 grams, and the same specific heat of 4.189. So when we multiply all this stuff out, we get the total energy is 173,636 joules. The energy of sample 1, the sample in the beaker, comes out to 2,041.792 times T, plus the sample that's added to the beaker has an energy of 28,618.56 joules. So then when we subtract the energy of sample 2 from the total, we find that it's 145,017.44 joules is equal to the temperature times the 2041.792, and then we divide both sides by the 2041, and we find that the temperature of sample 1 was 71 degrees Celsius. So there's your final answer. That got cut off a little bit again. Temperature is equal to 71 degrees Celsius is the final answer. Okay, 2.53 grams of butane, C4H10, are burned in a calorimeter with a heat capacity of 50 kilojoules per degree Celsius. If we know that the heat of the reaction is negative 2877 kilojoules per mole, so exothermic reaction, what will the temperature of the calorimeter rise to? So it's starting at 20 degrees Celsius, the temperature is going to go up. We need to figure out how much it will go up. So in order to do that, so up here we've got the heat of reaction equals negative 2877 kilojoules. That's per mole. So we need to figure out how many moles are being consumed here. So we've got a bunch of dimensional analysis conversions to do, and you can kind of do them all in a row to get the final answer. So we'll see how much room we have to string these through. But we've got 2.53 grams of butane. 1 mole of butane has a mass of 58 grams, and 4 carbons and 10 hydrogens. That gives me 0.043 moles times the heat of the reaction, which is negative 2877 kilojoules per 1 mole, which means we have 123.7 kilojoules that should be produced. So take that number down to here, and we multiply the amount of energy released by the reaction, 123 kilojoules, by the heat capacity, which is for every degree Celsius you need 50 kilojoules. So 123.7 divided by 50 gives us 2.46 degrees Celsius. So if the initial temperature was 20, then the final temperature would be 22.5 degrees Celsius if we round for significant figures. How does it go from negative here to positive in terms of the temperature change? You have to remember that the negative in this calculation is from the point of view of the reaction. So the butane is losing 123.7 kilojoules. That is being absorbed by the calorimeter. So from the calorimeter's perspective, this would be a positive 123 kilojoules. From the point of view of the reaction, which is usually how we look at things, it's a negative because it's losing heat to the surroundings. So that's why it ends up as a positive 2.5 degrees of increase. Okay, well, we got a bunch of stuff to do here with a Hess's law problem. We've got 4 equations to work with to get our final equation. We've got all the heats of reactions. So with these problems, the first thing you need to look at is which side of the equations that you're working with have, or which equations have the reactants and the products that you want in your final equation, and on which side. So the first thing I'm going to notice, and I'm going to zoom this in here a little bit for a minute. The first thing is I've got 2 aluminum solid as a reactant in my final equation. In this first equation up here, I've got 2 aluminum solid on the left-hand side. Great. I'm not going to have to do anything to that equation, hopefully, because it's got the right number, 2 aluminum, and the aluminum is on the left-hand side already, so there's no flipping around. That's good. The next thing is the chlorine in the final equation down here is the second reactant. And in this third equation, I have chlorine gas on the left-hand side. So again, I'm not going to have to flip it around, but I am going to have to change that equation because I need 3 chlorine gas, and I've only got 1 in the equation up here. So I'm going to multiply this entire equation by 3. And what that means is when the time comes, I'm going to multiply the energy of that equation by 3 as well. Okay, so you can just kind of like when you're balancing equations and finding coefficients to make everything line up, when you're doing these Hess's law problems, you can multiply or in even some cases divide an equation by some number that you need to make it work out, as long as you multiply or divide the energy by the exact same amount, and it's all proportional, so that can work out. Alright, so the next thing is my product is the aluminum solid. Well, in this bottom equation I have aluminum solid, but it's on the wrong side, so that equation is going to get flipped around. And when you flip that around, you're also going to flip around the sign of the equation. And in this case, I need to flip it around, and I also need to multiply it because I need 2 aluminum solids and the equation only includes 1. So I'm going to multiply this equation by 2, which means I'm going to multiply the energy by 2, and I'm also going to reverse the sign because the equation is going to be reversed. So the last thing that I have here is that in the equations, the things that I need to cancel out, which this second equation doesn't have any of the reactants or products for my final equation, it's there because I have the hydrogen chloride gas and hydrochloric acid in the other equations, and I need to get rid of it. The same goes for the hydrogen gas in the third and the first equation. Those have to be canceled out. So I'm going to try to transpose now down to the bottom the equations that I'm going to end up with. So the first equation, again, that's going to be unchanged. So it's 2 aluminum solid plus 6 hydrochloric acid aqueous produces 2 aluminum chloride aqueous and 3 hydrogen gas. And that also has an energy of negative 1049 kilojoules. The second equation, I'm going to need to multiply by 6, okay, because I have 6 aluminum chlorides, hydrochloric acid here at the top in the first equation, and when I multiply this third equation by 3, my hydrogen chloride gas is going to become 6 as well. So for the second equation, I'm going to end up with 6 hydrogen chloride gas becomes 6 hydrochloric acid aqueous. And when I multiply the energy of that reaction times 6, I get negative 448.8 kilojoules. The third equation, again, I'm not flipping it or anything, but I did multiply it by 3. So that gives me 3 hydrogen gas plus 3 chlorine gas produces 6 hydrogen chloride gas. Okay, and when I multiply that heat by 6, I get negative 5,535 kilojoules. And then the last one, I had to flip it around and I had to multiply it by 2. So we're looking now at this up here, this bottom equation. If I flip it around, I get aluminum chloride aqueous on the left and aluminum chloride solid on the right, and I multiplied it by 2, so I get 2 of each. And then when I multiply the heat of the reaction by 2, I get 646. It started out as a negative, but since I flipped the reaction around, it becomes a positive 646 kilojoules. Okay, so I've got, in the first equation, I have 6 hydrochloric acids. In the second equation, I have 6 hydrochloric acids on the other side. So those are going to cancel each other out. In the second equation, I have 6 hydrogen chloride gas. In the third equation, I have the same thing on the other side. So those are going to cancel each other out. So that second equation is just completely canceled out now. It was just there to take care of the hydrogen chloride and the hydrochloric gas that was in the other equations. So the last thing here is, or the last two things, in the first equation, I have 2 aluminum chloride aqueous. In the bottom equation, I have the same thing on the opposite side, so those get canceled out. And finally, in the first equation, I have 3 hydrogen gas, and in the third equation, I have the same thing on the opposite side. So those get canceled out. So now that we've canceled everything that appears on both sides, what we are left with is 2 aluminum solid plus 3 chlorine gas produces 2 aluminum chloride solid. Okay, so those are here, here, and on the right hand side here. Those are the things that didn't cancel out. And that's what we had in our equation. That's what's left. That is what we wanted for our final equation. So all that's left to do is to combine all the heats of the equations that we used, all the steps essentially that it took to get from beginning to end. And when we do that, we get a value of 6,386.8 kilojoules as the final answer. Okay, so combustion of butane gas, which we actually had in a previous problem, is negative 2,877 kilojoules per mole. And if we're given enthalpy of formation of carbon dioxide and water, which would be the products, we can write the balanced equation and then figure out the heat of formation of the butane. And we're going to do that because the heat of the reaction is equal to the heat of the products, the energy of the products, right, minus the heat of the reactants, or the sum of the heat of the formation of all the products minus the sum of the heat of all the reactants, so heat of formation of all the reactants. Different color here. Here we go. So if we write out the balanced equation, we have C4H10 gas plus O2 produces CO2 plus H2O, and that is the reaction that produces the 2877, negative 2877. Let's get cut off. Now it's not balanced yet, so we have to balance it before we can do the math, because the numbers for the heat of formation here are per mole, so we need to know how many moles it is, and then we have to adjust the numbers accordingly. So to balance this, if we have 4 carbons on the left, we need 4 CO2s on the right. If we have 10 hydrogens on the left, we need 5 waters on the right. And I know what you're saying. We've got an odd number of oxygens. We've got 8 in the CO2, and we've got 5 in the water. We've got O2 on the left, so we're going to have to double everything. Well, that would be true if we were just trying to come up with the balanced chemical equation, which we are not in this case. So, as many times as I've told you, you cannot have fractions in your balanced chemical equation. That's still true, but we're using the equation for something else. So, what we're going to do is we're going to put a 6.5 here, which would give me 13 oxygens. We could double all the coefficients. That would mean doubling the heat over here, and then in the end, when we wanted to find out the heat of formation of 1 mole of butane, we would have to divide by 2 again. So really, we're just saving ourselves a little bit of work here. And when we're talking about these sort of Hess's law type problems, that's okay, because it's not actually the balanced equation, it's the equation that gives you the heat there. So we know that the heat of formation is, or sorry, the heat of the reaction is negative 2,877 kilojoules, and that is the sum of the heat of formation of the products minus the sum of formation of the heat of the reactants. Well, so that means that 2877 kilojoules is equal to the heat of the products. So the heat of formation of 4 moles of CO2, so 4 times negative 393.5 kilojoules, plus the heat of formation of 5 moles of water, so 5 times negative 285.8 kilojoules, minus the heat of the reactants. Alright, so when we do that math out, we end up with negative 2877 kilojoules kilojoules equals negative 3003 kilojoules minus the heat of the reactants. And subtract on both sides. We've got negative 2877 minus 3003, or minus negative 3003. We end up with 126 kilojoules equals the heat of the reactants. Okay, so the heat of formation of butane gas is negative 126 kilojoules per mole. Well, wait a minute. What about the oxygen? If the heat of the reactants is 126, how do we know that that's the heat of the butane? Because oxygen in this equation is elemental, right? It's just oxygen. The heat of formation of any element is 0. So all of the heat of the reactants comes from the heat of formation of the butane. Why did I switch it from positive to negative? Because this calculation that we did here is looking at it from the point of view of the reaction, which is the reverse of the formation of butane, right? If we wanted butane as a reactant, as a product, we'd have to flip the whole thing around. So therefore, when I flip that around, this amount, the 126, has its sign flipped around, and we end up with negative 126 kilojoules. So the heat of formation of butane is negative 126 kilojoules per mole. All right, and I realized when I got this going that the image in the answer key here has all the things filled in, and I didn't write in which ones I labeled A, B, C, and D, but if you're looking at your practice test, you can see which part goes where. So the y-axis is energy. Okay, the reaction progresses from left to right. So the level on the left is the energy of the reactants. The level at the bottom right is the energy of the products. The difference between the energy of the reactants and the energy of the products is the heat of the reaction, the enthalpy. So if the products are above the reactants, that's an endothermic reaction. If the products are below the reactants on the energy axis, then you have an exothermic reaction. And this peak here in the middle is called the activation energy. That's the amount of energy it takes to start the reaction. So the reactants need a certain amount of energy in order to form what's called the activation complex, which would be right here. And once they reach that, then they can proceed to becoming the products. Okay, which of the following statements is incorrect? When the system, well, you can read these, I'm not going to read them to you. The one that is incorrect is the second one here. When the system does work on the surroundings, the work that the system is doing is pushing on the surroundings. When you push on the surroundings, you are expanding. So the volume change, so it pretty much had to be one of these two, right? But this is actually correct. So the question is, which one is incorrect? The one that's incorrect is that system doing work on the surrounding is a positive volume change. It increases. And a negative value for work because the system is pushing and working on the surroundings, which means it's losing energy, giving energy to the surroundings. Which of the following is correct? Well, work is the force a system exerts on its surroundings multiplied by the distance over which the force is applied. The other ones, this is the opposite of what's true. It would be a high specific heat. Activation energy is not the difference between the reactants and the products. That's the enthalpy. The activation energy is the amount of energy required to make the reaction go. And the activated complex is not the product or what's there when the reaction is completed. The activation complex is actually there right in the middle. So make sure you know your formulas. Okay, change in energy is heat plus work. Work is pressure times change in volume. You've got your mass times the specific heat capacity times the change in temperature. Understand your the heat of the reaction. So trying to remember which ones you need to know here. Heat of the reaction is the sum of the heat of the products minus the heat of the reactants. And those should be pretty much the ones you though. Some of the other information you might need, like specific heat and things like that, will be given to you as part of the test, so you don't need to memorize the specific heat capacity of water or anything like that. Any of those data points you need will be given to you. So there you go. The test will be on Monday. Good luck.